Welcome to the deep dive. Ever think about what's really holding our buildings up? It's the ground beneath us, right? And today we're diving deep into how structures and that ground actually interact. This field called soil structure interaction, or SSI.
That's right. When you first learn structural engineering, there's often this idea, this picture of the ground being, well, completely solid, an unmoving base.
Yeah, like a rock.
Exactly.
Yeah.
It makes the math simpler, for sure, but the reality is the soil itself plays a really crucial role. It's not just passive support.
Right. So our mission today is to sort of unpack that reality. We've dug through some lectures and a really useful FEMA webinar.
Yeah, that FEMA guide was interesting.
To figure out when this interplay, this interaction between a building and the soil becomes really critical, and why you should maybe have it on your radar. The big question we're trying to tackle is, when does the ground's own flexibility and its movement really change how a structure responds? Especially when something like, an earthquake hits.
Yeah, we're basically looking at when we can't just assume a building is sitting on an immovable object.
Right.
We need to consider that the ground itself can flex and move, partly because of the structure, and the structure's response changes because the ground isn't perfectly rigid.
Okay, so let's start with that picture most of us have in our heads. We often see a building as this single unit, maybe a weight on a spring sitting on a totally solid base.
The classic SDOF model.
Exactly.
Yeah.
And some of you might have even seen those SAP 2000 models, where the column bases sometimes have those little green springs shown.
Yeah.
That's kind of a hint at what we usually simplify away, isn't it?
It is. And that simplification, that idea of a fixed base, it's just that an assumption to make things easier to analyze initially.
But it's not real life.
Not always. No,
Yeah.
Soil isn't infinitely stiff. It has its own elasticity, It can absorb energy that's damping, and crucially, it can deform. It moves.
Right. Think about a building's foundation. In that simple fixed base model, it's just glued in place. But in reality, that whole foundation mat or footing system, it can shift sideways a bit. It can rock back and forth.
Absolutely. That fixed base idea just doesn't capture all that potential movement right there at the ground level.
And that's precisely what SSI is trying to address then.
Exactly. It recognizes the ground isn't just passive support, it's an active part of the whole dynamic system. Now, the key question, like you said, is when does this active participation really make a difference in the numbers?
Okay, so when does thinking about SSI go from being just, an interesting academic point to something we actually need to calculate and worry about in a design?
Well, the sources we looked at point to a couple of key scenarios.
Okay.
The first one is maybe the more intuitive one. If you have a relatively flexible structure, think tall and willowy, built on very stiff soil like rock or really dense ground.
Right.
In most of those cases, the effects of SSI are generally not that significant. The ground is just so much stiffer than the BL.
So like those really tall, slender skyscrapers or maybe long-span bridges.
Yeah, exactly. Or even things like big tanks holding liquid if they're on really dense soil, where seismic waves travel super fast, maybe faster than, say, 300 meters per second.
Okay.
In those situations, the stiff ground pretty much dictates the behavior. The interaction doesn't change the overall picture dramatically.
Got it. So stiff ground, flexible building SSI,
Sure.
maybe not a huge deal. What's the other scenario?
Okay, the second scenario is where it gets really interesting and maybe a bit counterintuitive for some folks.
Oh.
It's when you have a stiff structure, maybe a shorter shear wall building sitting on relatively soft soil.
Okay, stiff building, soft soil.
Yeah. And that's when considering SSI becomes very important. And surprisingly, it can often be beneficial for the structure.
Beneficial. How does that work? I mean, you'd instinctively think soft soil is always worse, right?
Well, yeah, that's the common thought. But by actually accounting for SSI, when you have this stiff building on softer ground, you can often see a decrease in the forces the building is predicted to feel during an earthquake.
A decrease. Why?
It happens because the softer soil allows the foundation to move in more ways. It can rock more easily, it can slide a bit horizontally, maybe even twist.
Okay.
And these movements, these extra ways the system can deform, they actually help dissipate some of the earthquake's energy that would otherwise go straight into damaging the structure itself.
Ah, so the ground is acting kind of like a natural shock absorber in that situation?
Yeah.
Taking some of the hit?
That's a great way to put it. Exactly. What SSI does in this scenario is it increases the predicted natural period of the whole system. The building and the soil together sway slower.
Right, the period gets longer.
Yes. And it also increases the overall damping in the system. Damping is basically how quickly vibrations die out.
Okay. More damping is usually good in an earthquake.
Usually, yes. So a longer period and higher damping mean the combined system is less likely to resonate, to really get shaken hard by the most damaging frequencies in the earthquake. Less energy ends up impacting the building itself.
Okay, that makes sense now. So these different ways the foundation can move, you mentioned sliding, rocking. What else?
Well, there's vertical movement, sometimes called pounding, if the foundation lifts off and slams back down. There's torsion, or twisting, plus the horizontal translations in 2 directions.
So potentially 6 ways it can move, 6 degrees of freedom.
In a really detailed analysis, yes. These different modes of deformation, they all provide mechanisms for the soil structure system to absorb and dissipate energy that would otherwise cause stress and potentially damage within the building's frame or walls.
Right. And by accounting for these mechanisms, we get a more realistic picture of how the building will actually behave.
Exactly.
And potentially, getting that more realistic picture could mean we don't have to over-design things quite so much. Maybe save some costs by not needing to make the structure unnecessarily strong.
That's definitely a key potential benefit, yeah. Avoiding unnecessary conservatism.
But it sounds complicated. You mentioned 6 degrees of freedom.
It can be complicated. It's important to realize that a full SSI analysis can get quite detailed. Even the simplified models we often use in practice are still more complex than just assuming that fixed, rigid support.
Okay.
But we can kind of break down this complexity into 2 main types of SSI effects, conceptually.
All right, what are those?
The first is called kinematic SSI. Think of kinematic as relating purely to motion without considering forces yet.
Okay.
This refers to the fact that a stiff foundation, like a big concrete mat, just can't bend and deform in the exact same way the free ground around it would have moved during an earthquake if the building wasn't even there.
Ah, so the foundation is too stiff to follow the little wiggles in the ground motion.
Kind of, yeah. There's a mismatch. The rigid foundation averages out or filters the ground motion it feels compared to a single point in the free field. It's like a disagreement in motion between the stiff foundation and the more flexible soil.
Okay. Kinematic interaction, the motion difference. What's the second type?
The second is inertial SSI, and this is where the building's mass and its movement come into play.
Inertia. So the building's tendency to stay put or keep moving.
Exactly. As the building sways back and forth, its inertia creates forces at the foundation level. These forces then cause deformations in the supporting soil, rocking, sliding, the things we talked about. It's the effect of the structure's mass and vibration acting on the soil.
So kinematic is more about how the foundation receives the motion from the ground, and inertial is about how the building's response then affects the ground.
That's a pretty good way to think about it, yeah. Kinematic affects the input motion. Inertial affects the system's dynamic properties like period and damping due to soil deformation.
Okay. So when engineers actually need to analyze this stuff, how do they do it? What are the approaches?
Broadly, there are 2 main paths. The first is what's called direct SSI analysis.
Direct.
This involves using powerful computer methods, typically finite element analysis or maybe finite difference methods, to model the entire system, the soil, and the structure all together in one big, complex model.
Wow. Okay. That sounds intense.
It is. It's very computationally demanding and often the kind of thing you see in PhD research. Getting the meshing right, especially where the soil and structure meet, can be a real challenge.
I can imagine. So what's the alternative if you're not doing a PhD?
The second approach, which is much more common in everyday engineering practice, is the indirect or substructure SSI analysis.
Indirect or substructure, how does that work?
This method simplifies things quite a bit. Instead of modeling the whole soil domain, it represents the soil's effects on the building using simpler components. Usually, these are springs and dashpots placed at the foundation level.
Ah, springs and dashpots, like in basic vibration examples.
Exactly like that. The springs represent the stiffness of the soil, how much it resists deformation, and the dashpots represent the damping, both the material damping in the soil itself and that radiation damping effect.
Radiation damping, remind me what that was.
That's the energy that dissipates away from the foundation as seismic waves travel outwards into the soil mass. It's like the energy just radiates away and doesn't come back to shake the building more.
Got it. So the substructure method uses these springs and dashpots to mimic the soil's behavior without having to model all the soil explicitly.
Precisely. And that FEMA P 2091 guide we mentioned, it heavily focuses on this substructure approach, getting practical ways to calculate those spring and dashpot properties.
Okay, that sounds much more manageable for design offices. But how do you figure out the right stiffness and damping for those springs and dashpots? It must depend hugely on the type of soil, right?
Absolutely. And that brings us to how we model the behavior of the soil itself. Because soil isn't just one thing.
No, definitely not.
We often talk about linear versus nonlinear soil behavior. Linear behavior is the simpler assumption. It assumes that the soil's properties, like its stiffness or modulus, its damping capacity, and how fast seismic waves travel through it all stay constant, no matter how much the soil is strained or deformed by the earthquake or the structure.
But real soil probably doesn't behave quite that neatly under strong shaking, does it?
Generally not, no. Especially softer soils.
Yeah.
Nonlinear soil behavior acknowledges that these properties change. As the soil strains more, its stiffness typically decreases and its damping often increases. And if it's strained a lot, it can even degrade or lose strength.
Okay, so nonlinear is more realistic, but probably harder to analyze.
It is. So in practice, particularly for SSI within the substructure method, engineers often use something called an equivalent linear SSI analysis.
Equivalent linear. I think I've heard that term used for site response analysis too, how the ground layers themselves shake.
It's a very similar concept, yes. It's an iterative process. You start with some initial estimates for the soil stiffness and damping, maybe based on low strain measurements. Then you run the SSI analysis and see how much strain the soil actually experiences near the foundation.
Right.
Based on those calculated strains, you adjust the soil stiffness, usually lower it, and damping, usually increase it, using standard curves developed from lab tests.
And then you run the analysis again with the new properties.
Exactly. And you repeat this cycle, calculate strains, update properties, reanalyze until the properties you're using are consistent with the strain levels you're calculating, until it converges.
So it's a way to approximate the nonlinear behavior without doing a full, complex nonlinear analysis.
Precisely. It captures the most important effect, which is the strain dependence of stiffness and damping.
Okay. And that FEMA P2091 guide, a practical guide to soil structure interaction, helps engineers do this.
Yes, that's its main goal. It's specifically designed to help practicing engineers understand and apply the SSI requirements found in building codes like ASCE 7, which covers new buildings, and ASCE 41 for seismic evaluation and retrofit of existing buildings.
So it tries to make SSI less intimidating and more accessible, using those spring-based substructure models.
Exactly. It provides step-by-step procedures, equations, charts, and, importantly, worked examples. It translates the complex theory into practice.
Is that the main resource, or are there others?
It's a key practical one. For a more in-depth academic background, the sources also mentioned a big report from NICE peer, led by Professor John Stewart, which compiled a lot of the research basis for current SSI provisions.
Good to know. Okay, so drilling down a bit more, what are some of the really key terms or specific phenomena within SSI that engineers need to grapple with? You mentioned radiation damping.
Right. So damping is key. There's the soil material damping, often called hysteretic damping, that's energy lost due to friction and rearrangement within the soil particles themselves, similar to damping in the building structure.
Okay.
And then there's that radiation damping, which is unique to the soil foundation system, energy radiating away. Both contribute to the overall damping represented by the dashpots in the substructure model.
Got it. What else?
Another important concept, particularly for the kinematic part of SSI, is base slab averaging.
T-slab averaging. Okay, what's the idea there?
The idea is that if you have a large foundation, like a big mat foundation covering the whole building footprint, or maybe a grid of interconnected footings,
Right.
the ground motion it experiences isn't just the motion at a single point. Because earthquake waves aren't perfectly uniform, different parts of that large foundation will experience slightly different ground motions at any given instant. They might be slightly out of phase or have different amplitudes.
Ah, so the big slab kind of averages out those small variations across its area.
Exactly. It filters out some of the high-frequency, less correlated parts of the ground motion. The net effect is usually a reduction in the overall translational and rotational motions that the foundation experiences, compared to what a small single footing or just a point in the ground might feel.
Does this depend on the size of the foundation?
Yes, very much so. It's more significant for larger foundations and also depends on how fast the shear waves travel through the soil. Slower waves mean more variation over a given distance, so more potential for averaging. This effect requires the foundation elements to be well connected, though.
Makes sense. And this is based on observations?
Largely empirical, yes, though there's theoretical work too. Then we also have embedment effects.
Embedment. So how deep the foundation is buried.
Right. This relates to the observation that generally the intensity of ground shaking tends to decrease as you go deeper below the ground surface.
Okay.
So if a foundation is significantly embedded into the soil, it might experience less intense shaking than it would if it were right at the surface.
Does this also depend on the soil?
Yes, the depth of embedment matters. And again, the soil's shear wave velocity is a key factor in quantifying the reduction. Interestingly, that FEMA guide suggests there's a practical limit to this benefit. They seem to cap the effective embedment depth you can consider at around 20 feet or so.
So digging deeper than 20 feet might not give you much extra credit in the calculations, according to the guide.
That seems to be the practical guidance, yeah. Perhaps diminishing returns or uncertainties beyond that depth.
Okay. Now, is there a quick check, like a rule of thumb, to get a feel for whether we even need to bother with the inertial part of SSI for a specific project? The part related to the building's mass affecting the soil.
Yes, FEMA P2091 offers one, and it's quite useful as an initial screening tool. It involves calculating a specific ratio.
A ratio. What's in it?
Okay, you need 4 things. The building's fundamental natural period, let's call it T.
Okay. How fast it sways.
The effective shear wave velocity of the soil beneath the foundation, V's.
How stiff the soil is.
The building's effective height, he.
How tall it effectively is for vibration purposes.
And a characteristic dimension of the building's base, like its width, V.
Okay, period. Soil velocity, height, base width. What's the ratio?
You look at the ratio of T divided by V divided by he divided by VB, or sometimes written as TV, VC. If this overall number comes out greater than about 0.1, it suggests that inertial SSI effects are likely to be significant and should probably be considered in the analysis.
Greater than 0.1.
Oh.
Okay. How do we estimate that effective height, he?
For typical multi-story buildings, a common rule of thumb is that the effective height is about 2/3 of the total building height above the base.
Okay, 2/3.
But one tricky point our sources noted is that there can be some confusion or inconsistency, even within codes like ASCE 7, about exactly how to determine that effective shear wave velocity, V's.
Oh, how so?
Well, often what's readily available is the VS30 value, which is the average shear wave velocity in the top 30 meters used for site classification. But the V's needed for SSI should reflect the soil stiffness right under the foundation, and it should ideally account for the strain levels caused by the earthquake. These might not be the same as VS30.
So using the wrong soil velocity value could really change whether you pass that 0.1 threshold or not.
It absolutely could. It highlights the importance of careful geotechnical input for SSI analysis. It's not always straightforward to nail down that V's value correctly.
Yeah, it seems like getting the inputs right is half the battle. Now, you mentioned the FEMA guide has case studies. Do they help illustrate how all these pieces fit together?
They do, yeah. There are a couple of detailed examples in there. One is a 2-story building with buckling restrained braces, which is relatively stiff.
Okay.
And another is a 10-story building with a dual system, meaning it has both moment frames and shear walls.
And what do these examples show?
They walk through the calculations for figuring out the soil springs, vertical, horizontal, rocking, incorporating the soil material damping and the radiation damping, and applying reductions due to base slab averaging and embedment effects.
So put numbers to all those concepts we discussed.
Exactly. And they show the impact of including SSI.
And what is the typical impact in these examples?
One key finding is that including SSI, particularly the inertial effects, often leads to a noticeable reduction in the calculated seismic forces on the structure. The spectral accelerations the building is designed for can go down.
Especially for certain types of buildings.
Yes, the reductions tend to be more significant for stiffer, shorter period structures, and also for the higher modes of vibration of taller buildings.
But there are limits, right? You mentioned codes cap the reduction.
That's right. The codes, like ASCE 7, usually put floors on these reductions. For instance, the final design forces often can't be reduced below, say, 80% of what you'd calculate for the same building on a rigid base, fixed base analysis. Or sometimes there's a limit relative to the original mapped seismic hazard values, maybe 70%.
So even if your fancy SSI analysis says the force is only 50% of the fixed base force, the code might say, nope, you have to use at least 80%.
Pretty much, yeah. It's a way to maintain a baseline level of conservatism, acknowledging the uncertainties involved.
Okay. What else did the case studies show?
They reinforced the idea that stiff buildings on flexible soils are the ones most significantly affected by SSI. That ratio of the structure's stiffness to the soil's stiffness is key.
Right, the scenario you highlighted earlier.
Mm-hmm. They also demonstrate how the foundation flexibility increases the building's overall period and damping. This shift in period can be beneficial if it moves the building away from the peak of the earthquake's energy.
But not always.
Not always. If the shift happens to move the period closer to a strong frequency in the ground motion, it could potentially make things worse, though often the increased damping helps mitigate that.
It's complicated.
It is, and one subtle but important point they bring up is related to damping. When you account for foundation damping, radiation damping, etc., you need to base those calculations on the building's period, including the foundation flexibility, the longer flexible base period, not the shorter fixed base period.
Ah, okay. Using the wrong period would give you the wrong damping estimate.
Correct. So overall, the examples show SSI can really change the numbers, usually leading to some reduction in demand, but you have to follow the procedures carefully and respect the code limits.
It sounds like most of the time, SSI might be slightly beneficial or neutral in terms of design forces, especially with those code floors.
In many common scenarios, particularly in places like California where code development has heavily focused, that might be the case, but not always.
Ah, okay. Which brings us to the big counterexample.
Exactly. We really need to talk about the 1985 Mexico City earthquake. That's just such a clear and tragic example of where SSI had a major detrimental impact.
Right. What happened there? What was unique?
Well, the geology of Mexico City is highly unusual. Much of the city is built on the bed of an ancient lake filled with incredibly deep, soft, water-saturated clay layers. Very, very soft soil.
Okay, extremely soft soil.
And these soft clay layers acted like a giant bowl of jelly during the earthquake. They massively amplified the incoming seismic waves, particularly those with longer periods. The ground shaking at the surface was much stronger than on the surrounding rock sites, and the dominant period of the shaking became very long, around 2 to 3 seconds.
2 to 3 seconds period for the ground itself. That's really slow shaking.
Very slow, yes. Now, consider mid-rise buildings, say in the 10 to 20 story range. On a normal, stiffer site, their natural periods might be shorter, maybe 1 to 1.5 seconds.
Okay.
But when these buildings were built on Mexico City's ultra-soft clay, the soil-structure interaction affects the foundation flexibility, significantly increased their natural periods.
They lengthened their periods.
Exactly. It lengthened their periods right into that 2 to 3 second range where the ground shaking was already massively amplified by the site conditions.
There, the building started swaying in perfect rhythm with the already super strong ground shaking.
Precisely. It created a devastating double resonance effect. The soil resonance amplified the shaking, and then the SSI effect tuned the building's periods into that amplified shaking range.
And the result was?
Widespread collapses of buildings in that specific height range. It was catastrophic. It showed, in the most dramatic way possible, that SSI isn't always beneficial. Site-specific conditions and the nature of the ground motion are absolutely critical.
Wow. That's the complete opposite of the scenario where SSI helps dissipate energy and reduce forces.
Absolutely. The Mexico City example is the ultimate cautionary tale. It tells us that how SSI affects a structure is intensely dependent on the specific site geology and the characteristics of the earthquake shaking. You cannot assume it's always good or always bad.
So wrapping up this deep dive then, what are the main takeaways we should leave people with about soil structure interaction?
Well, I think the first thing is just acknowledging that SSI is a complex but really important part of structural and earthquake engineering, especially in seismic zones, obviously, but also just for understanding how structures behave.
Right. Even though we often simplify it when we're first learning, the way the building and the ground actually interact can significantly change how the building responds to forces. It's not just sitting on a static platform.
Exactly. And we've seen it can be beneficial sometimes, right? By increasing the system's damping and lengthening the period, it can lead to lower forces getting into the structure.
Which can be good for design efficiency.
But then we have the Mexico City lesson. It can also be detrimental, tragically so, if it shifts the building's response into resonance with really strong site-specific ground motions.
So it's really crucial for engineers to understand when they need to seriously analyze SSI. You mentioned, for example, soft soils, maybe heavy concrete structures, or perhaps tall, slender buildings where rocking might be significant.
Yes, those are definitely key triggers. And the good news is there is practical guidance out there, like that FEMA P2091 document, to help navigate the complexities using the substructure method with springs and dashpots.
So the big mental shift is to stop thinking of the ground as just a passive support.
Right.
And start seeing it as an active participant, a dynamic part of the whole structural system.
Perfectly put. It interacts, it influences, and it's influenced by the structure.
And for listeners who want to dig even deeper, where should they look next?
Well, definitely check out the FEMA guide if you're a practicing engineer. For more academic depth, looking into research papers, people like Gazetas have done foundational work on foundation vibrations and impedance function.
Okay.
And for those with really deep technical interests, exploring advanced numerical modeling, like those direct SSI methods, could be a path.
Got it. So maybe a final thought to leave everyone with, thinking about the future.
Yeah, maybe this. As our cities keep growing, especially in earthquake-prone regions, and we're building on increasingly diverse and sometimes challenging soil conditions, how might a more widespread and deeper understanding of SSI actually change our future building codes? How might it influence design practices day to day?
Will we rely more on these analyses? Will the rules change?
It's definitely something to think about. How do we best account for this complex interaction to build safer, more resilient cities?
That's a great question. Thanks for joining us for this deep dive into the fascinating world of soil structure interaction. Until our next exploration, keep questioning the foundations of the world around you.